Good afternoon and good morning, everyone. I am Bobby Harris. I'm the Executive Director of the Utility Broadband Alliance, and it's my pleasure to welcome you here today for another UBBA member-sponsored webinar. Today, we're very fortunate to have one of our founding members, Itron, share their insights and perspectives on AMI 2.0 applications, and really to give a follow-on conversation from Kansas City when we were there last month at the UBBA Summit and Plug Fest. We were really fortunate to have their team there. So remember, for all of you attendees, that you can use the questions function of your GoToWebinar toolbox and type in your questions for the panelists. We'll save time at the end and we'll get to as many of those as possible. Tracy will actually read their questions exactly as you type them, so remember that. And feel free to do that. We'll have time for that. If we don't get to all the questions, as always, the team will follow up with you specifically if needs be. So we won't worry about that too much. Again, it's my pleasure to welcome Itron to this sponsored webinar. And Tracy Morales, please take it away.
Great. Well, welcome everyone. Thank you so much, Bobby and UBBA. Itron is really pleased to be here presenting today, as Bobby said, about utility AMI 2.0 applications. And really, we're going to be taking a deep dive into network considerations and architecture considerations. And so let me do a quick round of introductions with the speakers. We've got Carson Zerpa, Senior Business Growth Manager, Jan Forslow, Senior Solution Architect, and Oleg Pakovits, Senior Product Marketing Manager. And again, they will be presenting today. We look forward to your open dialogue and your questions. And so without further ado, I am going to turn it over to these gentlemen and take it away, please.
Thank you, Tracy. Yeah, so we were thinking how to structure it, and we created 4 sections. If we look at the next slide. So I will take the first one, which is a little bit just lessons learned from AMI 1.0, just to have that as background. And then Carson will take over and go through the AMI 2.0 use cases and benefits. And then Oleg will take the third section about network considerations for AMI 2.0. And I will come back with the final architecture considerations. So if you go into lessons learned from AMI 1.0, then, and you can go to the next slide. Then if we start with the use cases, those were, few categories, not too many. Meter data collection was definitely the biggest one, and maybe we started even with daily, but went quickly over to hourly readings. But now maybe we see like 15 minutes reads roughly, and the desired outcome was really to have 100% of all the meter data read from 24 hours. And then we had a few use cases, which was remote individual reads and remote comms on top of that. And then a fairly big use case area, which outage management, both outage notification and outage restoration. And this one probably was the most tricky in AMI 1.0 because we had sort of 60, 75 seconds to be able to send information from a lot of meters than if there was a larger outage. And that little time actually was often shortened by momentary outage delay, that you don't want to send maybe the first 20 seconds or similar, waiting out and see if it resolved itself. So that time of trying to send a lot of data, a lot of small data from all the meters in the sector or similar, that was like really stressing a little bit the system solution. So we'll come back to that because in AMI 2.0 we see this pattern more frequently as well. And then we have firmware over the air itself. We said here like an average 1 megabytes, try to achieve that across the population in 3 weeks. Now this, as we will go in more to AMI2 type of meters, you know, they are a little bit more computing intensive, has a Linux OS and so on. So even though we and other vendors are trying to make as much incremental firmware update as possible, this one can increase significantly versus 1 megabyte in certain cases if you need to do more upgrades of the OS itself and so on. So that's a little bit where we were on use cases and success criteria. And then if we look at architecture in the next slide, we had 2 architectures mostly using. One was like a mesh with an LTE backhaul. Often that LTE backhaul was a Cat1 or higher rate of LTE, and often set up so that there were sort of alternative ways through access points up through the network, so you could have a secondary path prepared and go to. And the cells were pretty large, like I wrote here, 1 to 4,000 per cell of mesh radius. And then we had the contrast, which was also deployed in with AMI 1.0, which was using a Cat M1 direct connect all to the meters. And in many cases, then we shared a bit of the capacity with other devices. So that's why you see so the red and blue icons underneath there on that architecture. And also here we saw similarly 1 to 4,000 per cell or per sector. And just experience-wise, we often got like 1 channel for Cat M1 usage, and maybe gives out like 30% of the max 1 megabyte capacity and megabits per second capacity. And you know, a little bit conservative here, but actually what we had to tune to was more like 5 to 6 connection requests per second when we deployed, in order to not overload that portion. So those were the 2 architecture we have. And if we look in the next slide of the sort of data reading schedules and how quickly that worked, then if you go full screen on the next slide. Like that, yeah, exactly. So then on this one, you can see the time it takes to complete the communication reading cycle on the vertical axis. And then you have some examples of different sectors or cells that were deployed, like going from dense urban 4,000 to very small ones. So it varies a lot. And you can see we put in a few different communication technologies. From the RF LAN was sort of the first generation mesh type of technology. And on the other side, the green one is Gen 5 mesh, which is the latest technology today that gets deployed. And in between there, you have Cat NB1, NB2, and Cat M1, which were different cellular technologies applied for AMI 1.0. And you can see really it's like Cat M1 and Gen 5 mesh. Those are the ones that could actually match even for dense urban, like for large sectors, like a 15-minute read schedule. So the other ones would actually not be able to run. They would more go up to like an hourly to fulfill those dense urban deployments. And of course, as always, you could solve this by either having more takeout points for a mesh type of architecture, or you would actually add more channels in a cellular system. And in some cases, we actually, in deployments, were able to get additional channels for a direct connect cellular system in order to cope with the capacity. So then, if we summarize in the next slide the AMI 1.0 sort of readout, and then how we will get to see how that maybe changes in the AMI 2.0. But for AMI 1.0, we ended up largely with 802.15.4G style of mesh networks with public cellular backhaul. That was largely driven by total cost of ownership, the aspect of getting a 20-year rate case where we didn't had to replace a large number of endpoints, and the desire in controlling this network. And we were not so pressured on like latencies or other things. So building a larger cell size is more acceptable. So we could build up to 1 to 1,000 or 1 to 4,000 access point to meter ratio. Regardless of architecture here, we did apply advanced application pacing in order to not overload the network. So this applies to both mesh and direct connect cellular. And this lack of good outage notifications, particularly in Cat M1 Narrowband IoT, was actually something that is not fully solved, I would say, in those initial architectures, and that needs to be worked more on. And it will come to fruition in here also in AMI 2.0 when we look at it. So that's a little bit background on the AMI 1.0, and Carson will now go over and describe a bit more the use cases and also the benefits of AMI 2.0.
Thank you, Jan. All right, go ahead and click to the next slide. So foundationally, the big difference, and I guess the gap, if you will, between AMI 1.0 and AMI 2.0 is where the sensing takes place. And even though when we look at it from a metering perspective, you're touching every meter and reading it in some batch, and in some cases, even AMI 1.0 meters were in 5 and 15-minute interval. The ability to time sync that and have it in a position where you can do true state analysis, there's a sizable gap, in which ultimately to do that, it was causing kind of a challenge between tying this data into real control systems and real engineering planning tools, and that would be the likes of the things that you would do kind of in the traditional centralized control model, which you can see today. When we look at how the data was being used with AMI 1.0, all the data was basically captured and sent centrally to a system. It would normalize that data and then it would be used in a planning exercise. And there were some control use cases, certainly outage and stuff like that. But the value of taking advantage of the sensing at the edge was minimized to the capabilities of the chipsets and the memory on the meters then. Why we pushed to the edge is clearly that as our consumers have evolved for the electrification of transportation and just electrification of the home, moving away from gas appliances to more electrical appliances for heat pumps and AC, electric cooking appliances and electric vehicles. The most dynamic portion of the grid is actually at the consumer front, and I think most utilities would agree that that's the case. And so that's foundationally why we realize that the investment to put the sensing capabilities and the final resolution data to understand what's happening behind the meter, to have that resolution data to accommodate that, and the ability to support communications and make decision and take action at the edge was foundationally going to help us kind of close the gap of visibility down to the consumer level, and in many cases to specific assets behind the meter. Next slide. So when we start to think about the new use cases that drive AMI 2.0, there's a suite of applications here on this slide, as you can see, and this is what we've got delivered in a handful of our utilities that have done this technology already. The core ones that we're going to talk about that are highlighted in red are tied to the stuff that we did with the UBA with PlugFest, but foundationally, there's a couple different buckets that utilities have been focused on, kind of the grid-centric use cases, like what they can do to have better state analysis, take action, better visibility and monitoring from a grid state perspective, as well as consumer style applications where you enrich data to enable consumer engagement, understand what the behaviors of these individuals are in real time, and then ultimately coordinate collaboration between consumer and utility in real time to better manage the grid. In the next slide, if you will, we'll talk about location awareness, which is kind of foundationally an application that most utilities have struggled with, since, and for those who know me well, I'm a distribution planner by training. I worked for Florida Power & Light for a number of years, and understanding the electrical connectivity is quite a challenging thing because of the distribution's dynamic nature. And so with the ability for these meters to in real time talk to each other, via PLC and RF, the ability to measure, not predict or not use statistics, but inject a signal and actually identify who is in fact on the same secondary bus to definitively group who's on the same transformer in real time is paramount for a lot of these control use cases that we're going to talk about here. And then certainly the ability to talk over RF with the other peers on other transformers to classify when they saw zero crossing, so they can assign where they are relative to A, B, C phase, also has a massive impact on supporting your load flows and energy management decisions or power flow decisions. So all this is embedded in this foundational application, which supports kind of the next suite of use applications we're going to talk about here in a second. Click on the next slide. So once we know, definitively how the meters are electrically connected, then there's this concept of kind of like spokes meter, or by using fog compute, all the meters can share data with each other, but one of the meters will leverage its processing capability to aggregate all the loading and voltage data from each of its peers. And so with that capability, you can minimize the traffic on the network for real-time monitoring, because one of those meters who is designated as the best communicator can ultimately push this data up on a 1-minute interval basis, or reporting by exception as well, of all the loading and all the voltage data in aggregation to that transformer. So you're effectively getting every minute your demand, your energy, your active energy, reactive energy, power factor, min, max, and average voltage. So you're effectively touching every single device in the system every minute, with the ability to put controls, control constraints relative to reporting by exception. So if you exceed load values or you exceed voltage values, you can alarm and push that data back, which gives kind of the first time kind of changing the paradigm in terms of using statistical models for load flow to actual taking measured values and injecting them into your control systems. And it's a foundational step that's actually evolving how we're integrating these tools into the control systems for AMI 2.0. Next slide. So in coordination with PG&E and part of what we did with PlugFest, how do we put this in action? So clearly, as we mentioned, the battlefront, associated to, or battleground associated to why the technology has been innovated is the interaction between utility and consumer, and the gaps relative to playing whack-a-mole, trying to chase down every new EV customer that pops up on your grid and making sure the infrastructure you have is ready to accommodate that new load. And so PG&E's concept was, if they could leverage, some rulings in the National Electrical Safety Code that allowed for real-time automation to throttle controllable loads to keep customers within their panel limits and service conductor and transformers within their limits, then twofold benefit. One, certainly there's deferred infrastructure requirements to the utility, also allows them to pace out the upgrading of their infrastructure, but it also provides an incentive for the customers to want to engage, want to interact with the utility, because foundationally what we found was that in their particular territory, in many cases they could defer panel schedule upgrades, which were several $1,000s. So the incentive for them to share data to be throttled when they're kind of their coincident peak at the premise level is going to exceed their rating of their panel schedule would save them thousands of dollars. And so this kind of marriage between the consumer and the utility dawned this application where the utility works with the consumer to real-time throttle these EVs to kind of stay within the layers of constraints that you could set in the meter itself. One that manages at the premise level, but then it manages from a teaming perspective by a peer-to-peer at the secondary bus and transformer level. And so we're quite pleased with the success we've had so far with the work that we've done with PG&E, and we're hoping to start to scale this early next year in the field. Next slide. So the continued innovation relative to hardware 2.0, or sorry, the AMI 2.0 hardware is clearly waveform data. It's leveraged for a number of different things, between consumer disag type of functionality as well as kind of grid sensor standpoints. And our approach, which is patent, it's actually patent pending, is that we apply rules to process waveform data at the meter, based on how we plot the voltage and current waveforms relative to these three variables, current factor, skewness, and ketosis. And depending on the change in the sinusoidal wave relative to those factors, we can make a fingerprint that kind of is indicative of different things taking place. And if you take the next slide, by leveraging the sensitivity of these new meters, which 2, 4, and 32 kilohertz, and processing this data in real time, the ability to trigger on these sine wave distortions, as you can see here, this is an example of identifying a cat bank that was impacting, that was causing harmonics on the service, was associated to basically both crest factor, skewness, and ketosis. All three factors were triggered on this, and so we were able to very strategically identify where these issues are, by who's impacted by them, and also categorize them like you would if you had a power quality recorder in the field. So we see that this is kind of the the continued evolution of how the utilities will be leveraging meters as sensors for grid sensors and for distribution management. And this is just one of several applications that we're doing with this, and inclusive of other things as well, as like tree contacts and wildfire prevention and things of that nature. All right. And with that, business case. So clearly there's got to be a reason for folks to want to don this technology. And I will preface this as the lion's share of the benefits, as you can see here, is tied to integrating this into real-time data and real-time control systems, whether it's for enhanced VVO or leveraging the aggregating capabilities at the transformer level to identify nested outage and reduce how you manage restoration and things of that nature. Primarily the lion's share happens to be on the real-time benefits associated with DI. I don't want to undersell the fact that the impact in terms of planning is significant as well, based on what we've seen with our customers in terms of business case. But the one thing that's kind of soft on this is then the 6% from a consumer standpoint is that 6% does not include the pieces that we were talking about relative to the value of the customers deferring upgrades to their electrical panel schedule. So that $35 per meter annually does not even factor the benefits associated to the consumer. These are just the cash in hand benefits relative to the utility. So we do think there's still quite a lot of value that's been left to be captured here. Again, and happy to coordinate with any of the utilities that are interested in looking into this technology more. All right. With that, I will hand it over to Oleg.
Thank you, Carson. All right, yeah, let's take a look at some essential network considerations when putting AMI 2.0 in place. And Tracy, if you flip to the next slide. So just to summarize here a little bit AMI 2.0, and this is this foundational difference between 1.0, as Carson and Jan also already mentioned. So this is the communication between the meters behind the transformer. So the meters, they need to, like, this is four essential use cases that are typically like sort of a base for realizing AMI 2.0, where the meters need to distinguish and exchange their location relatively to the transformer. Then also transformer load monitoring and load management and EV management. And so as you will see on this network needs, so the key takeaway here is that those meters, they need to be able to exchange the data within every minute. So which means there's a communication every minute or even more frequently between those meters to each other, and they need to exchange this data. And then when you saw the network topology, when we're looking at, let's say, public networks, what we have been testing, so and then we see up to 4,000 endpoints per cell. This could be quite a significant challenge on the network to accommodate all these connections with this very little data. So there's also communication to the head end, which is not as critical because it's not as frequently, but this is what we need to consider. And if we flip to the next slide. So here to show you the projection from 20 years back in the past and 20 years in the future. So basically what we looked at when we started deploying AMI 1.0 and the communication pattern in there. So when we started with like around 250 kilobytes per meter per month, where very essential data was exchanged with the head end Then we increased it slightly in 2010 by introducing some additional use cases. But in 2018, throughout now, we started deploying AMI 2.0. And this is where you can see that the data demand started growing. And then particularly so this red line, so this represents the data demand on the communication from the meter to the head end on the cellular side. And the gray line represents the communication between the meters. So this can be peer-to-peer, preferably, or of course it can go through the head end and then back, which is not especially efficient. And so with this projection, so we clearly recognize the challenge that we need to look at the network architecture to be put in place to support this use case, to support this growth. And when we flip to the next slide, so essentially we'll have like two potential architectures of the network. One is where the endpoints or the meters are connected to the network directly. This is like field area network. This can be private public network or private IP network. Or the second case is where the coverage extension or the clusters of the endpoints exchanging data between each other and communicate to the network only as needed basis. If it needs if the data needs to go to the head end. And so what we recognize is that with these use cases, what I projected before, around 95% data stays within this neighborhood area network. So the question arises, like, if it makes sense to use this architecture and send this data to the back end or to the head end, or to realize this architecture within FAN and NAN networking. So when we flip to the next slide, so yeah, so in that case, we will have a variety of options on the networking. When we say we have our 3GPP based networks, we have our mesh satellite PLC Wi-Fi. But the takeaway here is that there's no one size fits all. And so the future of networking, how we see it, will be in combining multiple different networks and managing them simultaneously or transparently to realize this AMI 2.0 use case and exchange of data. Going to the next slide. So, and this is where we focus on at Itron. So we call this intelligent connectivity framework, where we overarch the multiple networks, multiple different networks with the tool set to manage this network simultaneously. And this is when we look at cellular networks. This typically like connectivity management, there's remote SIM provisioning across multiple networks, device management, network profiling, and also security, last but not least. But also when we are looking at connecting this network, so like designing, architecting this network for solutions. So there's also two takeouts of data. This is one, IT, to manage this network, but there's also OT to manage, to receive and manage the data. So this is also needs to be considered in terms of security, in terms of secure tunnels across multiple networks. And so this is where we focus on. And when we flip to the next slide, so the interface to the cellular network, as we see it, this is the SIM card. So there's companies, people who build the networks, and there's company like who deploy solutions on top of these networks. So at Itron, so we are a solution provider, and we will build a solution to put on a deployed network. And our interface into this network is typically a SIM card. So now the SIM card can be a very standard SIM card with one carrier, and this can be private or public carrier, which will get the device on the network. Or in case of multiple networks, especially multiple 3GPP network, it might make sense to utilize the latest multi-network SIM technology or eSIM technology, and this is exactly what we do. So we are putting multiple networks on one SIM card, and by that connect to and utilize these capabilities of multiple networks. And so at this, I would like to hand back to Jan to to conclude this this summary.
Yeah, thanks, Oleg. So just some final architecture considerations then based on presentations so far. So we go to the next slide. Yeah, so in summary, we have this logically frequent peer-to-peer communication, and what it looks today and what the assessment is so far is that it's quite a heavy load of AMI 2.0 and some type of component where we can handle that locally. We call it the neighborhood area network here. Seem to be essential to have in an AMI 2.0 architecture. We should also recognize, like, even removing that logical peer-to-peer communication aspect, even the head-end to device traffic is increasing. So with the applications that we highlighted in red here for the UVA PlugFest, and we almost increase it by 10 times. So that is an increase to take into consideration as well. And maybe even more than that is, like, especially when it comes to control applications, like the management control application, we are more sensitive to have predictable latency. So we set the goal line a little bit here, like 5 seconds head end to device, in order to enforce a management control message. But in general, some of these AMI 2 applications are getting closer and closer to actually being part of sort of SCADA DA reliability, and as such need to consider resiliency in every portion of the network. So including what Oleg was explaining, like maybe you have private network, but you have public cellular fallback and so on, so you have resiliency at every place. And we didn't talk too much this year in the UVA activities about behind the meter comms. This one is essential though, like, it is in some of the use cases, like the EVSE management that Carson was describing, it is sub-second latency required on this home area network. And so far you see mostly usage of Wi-Fi there, but as Oleg was mentioning, also PLC type of communication can be very strong in this area. So that's a little bit of summary. And if we look at, if we should point in the next slide on any type of sweet spots for the future, we call it, like, or we mention it here as a sort of very small neighborhood and air network, which is maybe 1 to 100 when it comes to takeout point and a number of devices underneath it. So you see here, it's sort of going to some middle point versus where we started off here with AMI 1.0, where in AMI 1.0 we were a little bit more extremes. We had very, very large cells and access points handling that with open LTE and now lately 5G access into the cellular, or we had sort of direct cellular Cat M1 all the way to the meter. And both of those are a little weak, primarily for the AMI 2.0 in the whole classification, primarily for the very, very large mesh cells. The aspects to consider there is the sort of have a very predictable latency for management communication, and for the direct connect cellular is really how to handle the scale of peer-to-peer logical traffic and all the control signal coming with that. Those are sort of the weak points. And there's some benefits of finding this sweet spot, like, for example, the bullet number 3 there, like, in order to have a tool set which includes also a NAND component in the reach all the 100% of the assets, is a very good point to balance sort of the total cost of ownership of the deployment of a private LTE or private 5G network. Also balancing the rate risk, especially if you actually integrate some public cellular fallback, so that you don't have a rate risk on all the devices that you deploy, but it is on a subset of takeout points that you actually could consider in your rate case to upgrade ones. And finally, this could actually sort of smoothly evolve over time as you increase new applications coming up. And so then if you have more applications putting more stringent, for example, management control, you would add additional takeout points in the form of like socket access points that are color on the meter itself, or micro IPs even that are integrated in the meters in order to balance that correctly. So we can go to the next slide, and that discuss a little bit like looking in the future here, but a little bit of different NAND technology options. So here we show on the left side the Gen 5, which is the Itron version then of the AMI networking technology that is with mesh. And this one is good in some way in order to, for example, it has a direct peer-to-peer, direct one-hop routing for peer-to-peer, and it has a PLC with a nice broadcast capability that gets very good use actually in AMI 2.0. It has this long network life, which is really good for matching rate case. It could leverage customer investments that have been done so far, and then gradually flatten the network with app uptake. So it is very good go-to architecture for a NAND. But we also look at, can we find something that is a stronger, maybe standard? And one aspect that we have been working on alongside infrastructure vendors and so on is to look into an all 3GPP architecture for the future. And that would mean that we also try to solve sort of the NAND aspects for AMI 2.0 in 3GPP terms. And we have started, like, this sounds like it's long ahead, but you know, in 3GPP, 6G work has started with use cases, and we were working here already, and will continue to work on contributing our use cases into that standardization. And there is some good tie there. You know, some of the other applications like mission critical PDT has a little bit similar use cases where they also want to have direct hop routing between devices. So there is some use cases that actually can leverage maybe some development there in 3GPP. And then to the right, we have explored like the Wi-Fi, and specifically a variant of Wi-Fi called Wi-Fi Halo, which runs in the longer range 900 megahertz. Why we are interested in that is that, you know, there is a lot of blueprints for how to work with 3GPP between Wi-Fi and cellular. So that could be leveraged. It has a throughput level, which is good. It's sort of matching the 5G RedCap. And the last bullet there is, if we see an evolution and uptake on Wi-Fi Halo into the home and sort of the home area networking, we could find a synergy there. So right now, our go-to is to apply Gen 5 as the NAND, but we are actively working to look at alternatives also, like C, that we find always the best path over time. And we can go to the next slide, which sort of ties back a little bit what Carson talked about, and that is, we talk a lot about networking architectures, but there is a whole compute level architecture also needs to be considered here. The one that we are deploying so far, we call like a fog compute spokes meter model. And there are variants of here, but what we saw with this architecture so far is that we try to leverage all the processing power we have in all the meters. So we distributed the responsibility of processing across those. But we do have a spokes meter, which is a logical sort of level, so that we find who is the best person to coordinate among the cluster that is behind the transformer, and then be able to communicate also upwards towards the head end. And you know, right now one could apply a certain level of machine learning on every meter. In the future, it might go towards that there will be like a higher processing unit in the architecture, like the spokes meter or somewhere close to that, that has even higher performance for, you know, things like localized training, because you have to think about these devices are out there for 20 years, and for sure you need to retrain the models over that time quite a few times. And when you retrain, you need really like very high frequency data to do that properly. So outcomes by the spokes meter model is we can work and try to solve the core problems of extending life of medium voltage switching assets. We have the capability to be able to react very quickly with autonomous real-time edge optimization, and overall then reducing the burden on the back end, both from resources and cost perspective. So I think this is just showing where we are today and so on. This could be quite an interesting topic for UVB to work on as a core topic, and see architecture for computer architecture next year. So I think this rounds up our presentation, and we can, well, first of all, thanks everyone for listening in, but also can see if we have any questions that we want to tackle.
Thank you so much, gentlemen. That was fantastic. So let me see here. Give me one moment. I am going to check our question list here. Let's see what we have. I'm going to go off of sharing the screen here. Okay. Oh, this is an easy one. Is the webinar being recorded, and will the recording be available to rewatch? Yes, absolutely. Bobby will and a team will be sharing out the recording sometime in the near future after the event. Let me see if I can get to the next question here. I know there was another one about OpenADR. Bobby, I need technical assistance. Is there an easy way to scroll up in the questions?
Yeah, there should be a little slider on the side. I'll read the OpenADR one for you while you're looking for that. It was an early one. It said on EV chargers, are the control signals sent via OpenADR?
No, today, I mean, the way the architecture is set up, it's really, you can slide in any protocol over the transport layer from a Wi-Fi standpoint, but the protocol we're using today for EV charging between the meter and the device is OCPP over Wi-Fi. So an OCPP is Open Charge Point Protocol.
Thank you. Thank you.
Bobby, I don't see any other questions in the.
I can read them if your slider's not working. I apologize for that.
That's okay.
So yeah, a really good question here. There is an increase of data exchange with the AMI 2.0. What about meters powered with battery, meaning gas and water meters? Would this impact the lifetime of these devices?
I can take that a little bit. So at least what we have seen so far in terms of use case evolution, the use case and use patterns for gas and water meters and so on is a little bit more stable, I think. Like we, you know, the use cases that we had for AMI 1.0, and in those cases, it sort of stays and evolves a little bit the same. So it's like really like much more lift in general for the electricity side today. That's what we see. So if you look at our deployments and what we're doing a lot for gas and water, so if it's a gas or water only type of deployments, we do apply much more direct cellular in those cases because that's very efficient, especially for water. Maybe we don't have infrastructure either for sort of any pole mounting or similar for takeout points. So that's kind of architecture go through there. If there's combo utilities, then we still have the possibility to put in gas meters, for example, as leaves on top of that infrastructure of electricity, even in AMI 2.0.
Okay, thank you. One
Bobby,
other question. Yeah. Can you go? Do you see them now? Go ahead.
I do.
Okay,
So we got the we got the open ADR. There's lots of questions about sharing the slides. We'll share out, excuse me, a PDF of the material in addition to the recording. Did you get the one about, do you anticipate other neighborhood style applications that would take advantage of the NAN? One area that comes to mind is neighborhood security.
Yeah.
Do you want to take that, Carson, or maybe it's frozen? Yeah, like maybe I can talk a little bit. Like maybe we haven't explored it too much, but it is quite related, sort of some of the technologies, maybe at least the need for building up that kind of robust and low latency communication that you would like in the home area network. So there's potential definitely for coordinating with security, home security, and so on as well.
Well, to address this one also, so it's important to understand that this is not only on the communication on the device, but all the data needs to be routed securely. So which means if we are looking at different systems, the systems, they need to be interconnected, right, on the back end. And this is just a question of system integrator. So if the system integrator is working on these different systems, then it's probably easier. If this is independent systems, then it is probably more difficult on the data routing side.
Thanks, Oleg. It looks like this was a comment, so I'll read it and we'll get your gentleman's perspective. To clarify, there is no P2P communication for the GPPT solution, and location awareness is not possible. And if whoever made that comment, if they want to come off of mute, if that's possible, Bobby, and ask, have a conversation live, we still have enough time. I'm not sure where they were going with that exactly.
Yeah, otherwise we can take that later, but we can do that.
Yeah,
too.
let's do that for sure.
Sounds
If
good.
there's not an unmute. Go ahead.
Okay. I believe, oh, here we go. Is Itron committed to including OpenWay Riva customers as part of 2.0, such as those with OpenWay Riva meters, Cisco 1240 IR8140s, and 500W OpenWay Riva?
Yeah, I can answer a little bit in general. So Itron has been fairly good at migrating customers to the level where they can utilize it. There's of course a different levels always, like what the base meters are and so on, but we put quite a lot of effort into something we call it brownfield rather than greenfield, and that means like you're trying to enlighten sort of the networks, even if there are maybe meters that doesn't have like the processing power or the communication of PLC and so on in there. So we try then to lit up those network cells with individual units that goes out there, and they actually probe then the individual legacy units in order to provide certain aspects of AMI2 even in those cases. So we have this kind of gradual aspect, and particularly with Viva, we have migration plans and so on for customers in order to lift up so that they can get a strong AMI2 offering as well.
Thanks, Jan. And I would encourage whoever asked that question, if they have those networks and they wanted to have further conversation, reach out and we can definitely engage the right team to, have a roadmap discussion with you. We're happy to support that. Let me see what else we have. That might be the last question. That's the last one I see, Bobby.
That's correct. It's the last one I see also. If anyone else has a question, we do have a few minutes left. So you can type quickly into your question toolbox for the speakers. Okay. I think you hit on this. I'll ask a question while we're waiting on anyone on the audience. I think you hit on this a little bit, but maybe it kind of speaks back to the Riva question about AMI 2.0 integration, not only with other meters, but with grid infrastructure really, and third-party type software. I know that was kind of the hopes of some of the open architecture or open standards of AMI 2.0. Maybe talk just a little bit about that.
Yeah, that's a little bit the balance. Why we I was showing the slide that that we are looking at also future architectures where we could maybe get into an even stronger standard like 3GPP based NAND and so on. So there, we definitely recognize that this is a desire, and we are looking to see how that solves. Like for the current architecture with Gen 5, we do still integrate NIC cards and so on for that capability into third-party products so that it enables the ecosystem for it. One would say, and that's why I'm highlighting at the end, like communication is just one portion here. The compute architecture, distributed compute architecture, adds another layer of complexity a little bit in the whole question here. And so that is also something one have to work out and so on in terms of getting a fully plug and play system solution.
Beautiful, thank you. I think we have one more. Tracy, can you see that one? If not, I can read it.
Let me see here. I am not getting the last one. Do you mind, Bobby?
I don't mind. It might have come in faster on my system. I'll read it straight out also. It's kind of a three-part question, looks like. How do you see the optimum communication implementation for the LV meters, 5G combining public and private network, question, or 5G plus RF mesh network with cellular backhaul?
So probably, so I mean, either option works. And so we'll need to look at what's available, because so let's put it that way, private network is not always available, and then so it would make sense then use public and mesh. But when private network is available, then private public, this is we can put it together. So the combination of the components is kind of fairly flexible. So we'll need to look at the availability and at the capacity demand.
Perfect. Thank you. Okay. Well, we're about out of our time, and it looks like no other questions have come in. So I'll turn it back to you guys, Tracy, for your final comments before we wrap up.
All right. Well, gentlemen, before I help Bobby close us out, do you have any last thoughts that you want to leave everyone with?
Well, I mean, what we have seen, and we have worked on this AMI 2.0 for several years now, but even this last year with UVBA and the plug fest and so on, crystallized even more that AMI 2.0 is quite different. If you're a network engineer as me, it looked very different versus my 1.0, and I think we just have to realize that and work based on the use cases and then try to find optimal solutions from there.
Fantastic.
Yeah, I think just to add to that, so we are open for conversations, for discussions on different architectures of the networks. So, because at the end of the day, so the goal is to solve the real world problems, to reduce the load peaks, to make the energy delivery more efficient. And then how we achieve this is we are open to discuss. It's not like just one size fits all.
Thanks. And Carson, I think we lost you for a moment, but I see you back. Do you have any last thoughts before we close out?
I don't know if you hear my audio. Can you hear me?
Yes. Yep.
All right. Side connectivity issue. I apologize. Yeah, no, this was a good discussion. I think that the big thing is going to be the drivers relative to each utility has their own specific set of challenges, and how they deploy this technology will dictate the architecture and the applications that they prioritize. So.
Fantastic. All right, well, I won't keep you. I want to thank everyone for joining and thank the gentleman for sharing and thank UBBA and Bobby. And I hope everyone has a wonderful holiday season. And with that, Bobby, I'll let you close us out. Thank you.
Thank you so much. Thanks, Tracy, and thanks to the whole Itron team for sharing your insights. Again, you know, UBBA is all about collaboration for the good of the utilities, and this goes a long way in that. We appreciate the discussion and the sharing of knowledge. And if anyone's on the webinar is not yet a member of UBBA, please feel free to reach out at ubba.com, and I'll be glad to have a conversation with you. But I also hope you all have a wonderful and safe holiday season. Take care of each other and have a wonderful rest of your day. Thank you all very much for joining us today. Bye-bye
Thank you.
now.
Bye-bye.
Thank you.
Thank you.